Hey guys, so let's discuss new round from Google interview loop, and this is the round 3, and you can say coding round second. Okay, and so the question given to you is um, you have to create a course scheduling or topological sort. Okay, I means you would be given some courses. It's a prerequisite courses, and then you need to sort them. Okay, so this is what you need to do. Now here the first thing is you will clarify the requirement. Okay, this one will be the shorter one. Okay, we'll not discuss 10 or 20 follow-up questions here. We will be discussing few follow-up questions, and this is nothing but just related to Kahn's algorithm, BFS. Okay, so topological sort. So now first step is you will clarify the requirement. What you will ask them, that our course ID is unique. Okay, and then so let me describe you what we need to do. Let's say you have few courses, C1, C2, C3. Okay, but now there is a prerequisite that C3 you can take once you complete C1, right? So it means that you have a age from C1 to C3, and then you take C2 once you complete C3, so you have an age from C3 to C2. Okay, and there should not be any cycle. If let's say if here any cycle occurs, then it means that C1 you can take once you take the C2, then it will be a deadlock, right? So there should not be any cycle. And then you can see this, right, that what is topological sort. Topological sort is you have two vertices u comma v. Okay, if any age is going from u to v, then it in that case u is coming before v. Okay, this was the topological sort. If you remember, I have created video on graph. Okay, and there we have covered. So this is what we need to do now. See, so you will clarify the requirement very first thing. Okay, so you will ask that whether the course IDs are unique. Okay, then can there be a duplicate prerequisites, can the graph contain cycles. Okay, and then should we return only whether completion is possible, or also the course order. Okay, and then what are the limits on the number of courses and prerequisites. Now, because you can have a millions of prerequisites and courses also, so that graph would be very huge, and you cannot store that graph on one single machine. Then you need to take different machines, okay, to store that kind of graph. Now let's say if someone will change some courses, okay, update some courses, then the complete graph will get changed. Okay, so we will not do that. We will just update the part of the graph. Okay, and entire graph you do not need to rebuild. So this is what we handle this kind of situation. So now what L4 will say, okay, software engineer 2 in Google, we will be seeing answer based on L4, L5 and L6 round. Okay, so what L4 would be answering for this, so his expected answer would be, I'll model the problem as a directed graph where courses are nodes and prerequisites are ages. Okay, I will use Kahn's algorithm BFS to perform the topological sort and detect cycle. I will explain the algorithm, analyze its complexity and test it with the few edge cases. Okay, now the approach, what approach he will be following, this is normal graph question. Okay, so approach is Kahn's algorithm BFS. So you have a BFS DFS, so you will use breadth first search. Now, so idea is build an adjacency list. Okay, so the very first thing. Then second, compute the in degree of each courses, right? After that, add all the courses with the in degree 0 to a queue, and process the queue and reduce the in degrees. Okay, and if all the courses are processed, then scheduling is possible. So if you have processed all the courses, then you can say that yeah, you can schedule these courses. The graph is correct. So what he is saying, you would be given one adjacency list. So from that adjacency list, okay, you will compute the in degree. So for example, if you have something like this, C1, okay, C2, C3, and then C4, let's say, and the graph direction is something like this. Okay, so the in degree of C1, how many ages are coming inside C1? 0, right? So the in degree will be 0. What is the in degree of C2? It is 1, because one age is coming, right? This one. C3 1, C4 it is 2, right? From here. So now you will create one queue. Okay, you will create one queue and you will add all the nodes whose in degree is 0. So right now I can see only C1. Okay, so I will add C1 here. And then let's say you right now you have only one node. Let's say you have a 5 nodes, so you can take that 5 node, and then when you take out those nodes, so parallelly you can execute them. Okay, so here you can use the concurrency as well. Right now we have only one, so C1. Okay, now you will take out C1. Now when you are taking out C1, all its adjacent nodes in degree will reduced. Okay, because let's say the existence is not there. Okay, existence is finished of the C1, then the in degree should also modify, right? So this one will see 0 and this one will also 0. Okay, so that is what you will do. And now you have a in degree of C2 and C3 is 0, so you can add that in a queue. So C2 and C3, right? Then now you will take out C2. So as you're taking out C2, it's a adjacent means C4, so its in degree will become 1, right? After that you will take out C3, so again it's adjacent, its in degree will become 0. Now you will add C4 in a queue, right? And then you will take out C4 because C4's in degree is 0, right? So you will take out C4, your queue is empty, and how many nodes you have taken out? 4. Okay, and total nodes were 4, so 4 equal to 4, and your queue is empty, so it means that you can schedule these courses. Okay, so this is the normal logic behind it. Now if you see the time complexity, so time complexity, how many number of v you have, vertices and edges. Okay, so order of v plus e will be the time complexity, and space complexity again order of v plus e. Now where v is the number of courses and e is the number of prerequisites. Okay, now if you see the Java program, very simple. Okay, you have one class course schedule, then return true if all courses can be completed. Okay, 4 courses we have seen. Now you have one can finish method, okay, which is taking number of courses and then your adjacent matrix of the graph, right? Now first you will build the matrix. Okay, so you have given 2D array, means adjacent matrix, and from adjacent matrix you will create an adjacency list. Okay, so let's say your graph is of type list of list, and then till number of courses you will just put an empty array list into that graph first. Okay, and after that you will iterate, you will create one in degree array, okay, whose size will be number of courses, and initially it will be 0. And then now from this prerequisite, okay, this is 2D adjacent matrix. Now you will create a adjacency list. Okay, so 0 will be your course, and 1 will be on first. So let's say if you have given something like this 0 comma 1, so here 0 will come, 1 is the prerequisite, means first you need to complete 1 and then only you will complete to 0. This is what. Okay, so 0 will be your course and 1 will be your prerequisite, and then you will add that into a graph. So this is how you will create a adjacency list. Okay, and you will add it's a in degree. Okay, because initially you need to count the in degrees. Now after that, once you add all the element into the adjacency list, okay, add all the nodes with in degree 0, you will create one queue, and you will add all the nodes in a queue using queue.offer method, okay, whose in degree is 0. Now you will process queue one by one, you will take the element. Okay, so you will process initially completed courses are 0, and you will take out you will run this condition while your queue is not empty. Okay, so you will take the current value, first node from the queue. Okay, you will add you will just do the complete courses plus plus, because first course you have processed, and then after that all its adjacent neighbor you will go, you will check and just reduce its in degree. Okay, we have seen that if its in degree became 0, so you will add that again into the queue, and this process will continue until your queue is not empty. Okay, once your queue is empty, you will check whether the completed courses is equivalent to number of courses. Yeah, that's true. Okay, so in that case, this is your normal main method. Okay, let's say you have a number of courses 4, and so your 2D array is looking like this. Okay, 1 comma 0, 2 comma 0. So you will read it something like this, that you can start 0 once you complete, you can start 1 once you complete 0, something like this. Okay, now then if it is you can finish it, then just print it. So this is the normal Java program for this. Now senior software engineer, what L5, what he will be saying about it. I will first model the problem as a directed graph, explain cycle detection, then solve it using Kahn's algorithm BFS. Okay, so first he will check whether there is a cycle or not. Okay, and then he will solve it using the Kahn's algorithm BFS. Okay, I'll also discuss the DFS approach and compare both. Okay, so you don't need to discuss, but if you know, you can discuss that. I've created video on that as well. Okay, now staff engineer, what he will be saying, L6. Okay, so for production system, I would use Kahn's algorithm for static dependency graphs because it's easy to understand and detect cycle. Okay, for dynamic prerequisites, update or massive graphs, I would discuss incremental graph updates, distributed processing, and then memory efficient graph storage. So because let's say right now we have seen the graph which are very smaller in size. Let's say you have a very huge amount of very massive graph, let's say, okay, which you cannot store in one database and it is continuously coming. So there you will use the incremental graph update method. Okay, and then also distributed processing because now you have to store that graph in multiple systems. Okay, and then memory efficient graph storage. Now what do you mean by dynamic prerequisite updates? Okay, so like for example, initially your graph is 0, 1, 1, 2. Okay, let's later admin add new prerequisite 3, 2. So means your graph is changing, right? So instead of rebuilding the entire graph and returning topological sort from the beginning, you try to update only the affected portion of the graph. Okay, no need to rebuild again entire graph because of small changes. Just change that particular area, okay, where the new update is coming. So now what do you mean by massive graph? Okay, so massive graph means, let's say you have 10 million courses and 100 million prerequisite relationships. In that case, what you will do? Okay, so a single machine may not have enough memory or processing power, so the graph can be partitioned and processed across multiple servers. This is what I told you, horizontal scaling. Now let's talk about different follow-up questions. So follow-up question 1 is related to detect cycle. How will you detect the cycle? L4 will say, after processing the queue, if the number of processed courses is less than the total number of courses, it means cycle exists and it's impossible to complete all courses, right? This is what we are saying from starting on the number should equal. Then L5 will say, a cycle exists if we cannot process all the courses. If processed courses is less than total courses, a cycle exists. Same thing he is also saying. L6 will say, in production, log the nodes participating in the cycle. So to simplify debugging rather than only returning false, like whether there is any cycle exist or not, you need to log the nodes as well, okay, for the further process. Now follow-up question 2 is related to, can prerequisite change dynamically? Okay, so for example, L4 will say that if prerequisite change, I would rebuild the graph and run the algorithm again. Okay, now like for example, first you need to complete C1 and then only you can complete C2. Now instead of C1, I will change it to C3. Then in that case, what you will do, your complete graph will change, right? So L4 is saying that he will rebuild it. L5 is saying recompute the topological sort after update. So he will recompute it, the topological sort, right? If there exists a age from C3 to C2, in that case C3 will come before C2 in order. L6 will say, use incremental graph algorithm. So this portion he will update. Follow-up 3 is related to handle millions of courses. Okay, so how you will handle if you are getting millions of courses and millions of prerequisites, then what you will do? L4 will say that I would use an adjacency list because it's much more memory efficient than an adjacency matrix for a sparse graph. Now what is a sparse graph? Sparse graph, a graph with very few edges compared to the maximum possible number of edges. Okay, for example, you have 0, 1, 2, 3, 4 vertices, but if you see it's edges, okay, so it is just 1, 2, 3, only 3 edges are there. So this is a sparse graph. L5 will say that use adjacency list instead of adjacency matrix. That's why you have converted matrix to list, right? And L6 is saying that partition the graph across multiple machines. If billions of graph courses are coming, then partition it across the multiple machines. Okay, do the horizontal scaling if required, more servers. Now follow-up question 4 is related to parallel processing. So L4 will say that multiple courses with in degree 0 can be processed independently. I told you this, right? So they could be processed in parallel. L5 will say process multiple 0 in degree nodes concurrently. L6 will say workers process different graph partitions. Okay, now follow-up question 5 is memory optimization. So memory optimization, how you will optimize the memory. L4 will say I would use the adjacency list and avoid storing unnecessary information because most courses graph are sparse. Okay. L5 will say use adjacency list because they are required much less memory, that's why we have used it. And L6 will say compress node ID, lazy loading and streaming. Okay, so go with the compression of the course ID, node ID, and then do the lazy loading and then streaming. So that's it. Thank you.